We will now talk about applications of the theory that you have learned on mass transfer, basically the diffusion as well as the convection principles or theory to metallurgical problems. So we'll divide the next 3 lectures, including today's, to discuss 3 segments, mostly one with diffusive mass transfer, and here mostly I'm going to talk about the carburization, gas and box carburization process, carburization, nitridation, galvanizing. Also we'll see that a part of the galvanizing process. Galvanizing, you all must be knowing that it's basically the coating of iron with zinc for enhancing the life. So we'll discuss this. Then we have convective mass transport. And here we'll divide into 2 parts. In one segment we'll talk about dissolution of solids such as in alloying, and also I will talk about the topochemical reduction and topochemical reduction of Fe2O3. So iron ore reduction by carbon monoxide is a gas solid reaction, gas solid interactions, and dissolution of solids, that means a solid liquid interaction. And then about the convective mass transfer, I will talk about dissolution of gases in metals and also slag metal reaction. So this is what I intend to cover as far as the application of mass transfer theory is concerned. Let us talk about carburization first. And you must have all heard and learnt about carburization process, carburization of steel, particularly in your undergraduate heat treatment courses. And all of you may be knowing that carburization basically is a process. The objective of carburizing a sample, basically a steel sample, is to enhance the surface hardness. For example, there are many parts which are subjected to severe abrasion during applications. For example, you can imagine the gears, for example, which has teeth, and they're rotating. Their one gear is in continuous contact with another gear, and that's how the rotational motions are transferred into, say, horizontal motions, or the speeds are enhanced or reduced. And there, the teeth of the gear are subjected to enormous amount of frictional as well as mechanical resistances. So it is demanded that the bulk hardness may not be, if you use the bulk hardness of steel, that may not be suitable because of the large friction taking place at the point of contact. And therefore, it is warranted that the surface could be is at a higher, if you look at, so we are basically, we are not talking about, these are teeth, so these teeth needs to be, and at the most I need, some kind of a thick carbon layer here, such that the teeth also, are carbon rich. And you all know that in steel, when high carbon is present, more cementite forms, and cementite is a hard phase. So therefore, we don't want really carbon to reach here, and so the bulk hardness is not so important. Bulk has to be soft, okay, or as relative to the surface, but the surface requires enhanced strength, and that's what basically is done when you heat the samples or a steel sample in a carbonaceous mixture, and then allow the carbon from the surrounding to diffuse into the solid. And This is called the case depth. Okay? And this, depending on what is your criteria, you can say that, sir, I want that, at a distance of 0.5 millimeter, the concentration should be 75% of the surface concentration. Somebody may say 50% of the surface concentration, and so on and so on, so forth. And that will determine the case depth, which is a priori specified parameter. Okay? So I require that 1 millimeter carbon diffusion should take place, and at the edge of the 1 millimeter, the concentration is fixed. That also I have specified. And now the task is that if I put this sample in a carburization mixture in a furnace at a temperature, after what time should I take out the sample so that exactly, the same case depth has been obtained as has been desired. So that is the problem. And similar, I am going to simultaneously talk about the nitridation. Similarly, you can have a nitride phase also forming because of the nitrogen diffusion, which can enhance the hardness of the surface. And because this is happening from here, the transport of carbon and nitrogen is happening purely by a phenomena of diffusion. So that's why the process is slow. So the carburization, if you want to have 1 millimeter, 2 millimeter thickness, you have to carburize the samples or nitride the samples for a longer amount of time, in excess of several hours, for example, and then only. So they are the same principle actually, that nitrogen from the gas atmosphere will diffuse into the solid, make nitrides, and as a result of which what happens is that we can have surface hardness. Similarly, carbon from the surrounding can diffuse through the solid layer and make a carbon rich layer, which is basically cementite in steel, and as a result of which we can get enhanced surface hardness. Now, basically, carburization has two processes. One is we call as a box carburization. Many times box carburization, and this is basically some of you may have done your experiments. This is a standard experiment in undergraduate third year level physical metallurgy course actually. So you take a steel sample, put it in a box, and then we have pack it up with carbonaceous material, and then you heat it for some time, 1 hour, 2 hours, and then you take up the sample, and then you cut the sample and look at under microscope that to what region you are getting. So you could see this boundary very nicely. Okay? And there what happens, because carbon will be diffusing from all sides, so topochemical characteristics, that is the reaction front, okay, or the penetration depth in this particular case, will be moving inside in a symmetric fashion, giving the impression that the contour of the inside geometry, the interface, is having the same kind of a shape as the outer one. Okay? So the circular shape is going to be maintained. So there is a one-to-one correspondence between this geometry or this shape, or inside contour, with the outside contour of the specimen. So box carburization and gas carburization, these are the two processes that basically. So I hope you are able to see the problem that in industry what happens, you have to, I will give you everything and I will tell you that, look, you give me the time at which I should be able to take out the sample, and it should give me the exactly desired amount of case depth. And this can be done with the help of the diffusive mass transfer theories that we have really studied so far. Now, so box carburization basically will be, you take the sample could be a rectangular sample, and it is going to be put in a carbonaceous mixture. This could be, and then it is sealed from all, and there are certain, it is mixed, not just pure carbon, maybe there is sometimes sodium carbonate, etc. is also added, which is a carburizing agent, and as a result of which what happens is that carbon from the solid gets into carbon in the dissolved state. So this is pure carbon, activity is 1, and this is the surface concentration, and as I have indicated or said already, that this concentration, surface concentration, and then once the carbon reaches the surface, Okay? Then what happens? Then the diffusion process comes, and it is said that the rate of formation of or the rate of growth of the carburized layer is equal to the rate of the diffusion, carbon diffusion. So the chemical reaction is not the rate limiting step, so this reaction is at equilibrium. So this we can find out the surface concentration by invoking the assumption of an equilibrium. And the other case, so the reaction takes place, it is in a sealed environment, there is no oxygen there basically, okay? So therefore carbon, as the temperature increases, starts to diffuse. So you can have the problem basically, solve the problem in isothermal mode, but it is not going to be isothermal process because your sample would be at room temperature. You will be preparing the sample, okay, and then putting it into the box, covering it up with carbonaceous agents, closing the lid, and then putting it inside the furnace. So as you put it inside the furnace, then what happens? Temperature increases. Temperature of this mixture increases, temperature of this solid increases, and simultaneously carbon also starts to diffuse. Okay, this reactions takes place at the interface. So it is essentially a combined or simultaneous heat and mass transfer problem. But if you consider a lapse of some time, then you can consider that the mass transfer or diffusion is taking place essentially under isothermal condition. This is so because, as I have indicated, that the thermal diffusivity value is much greater than 1. It is of the order of 100. So heat is diffusing at a much faster rate than mass. So therefore this sample will attain if the furnace temperature is 1000 degrees centigrade, okay, in that case what happens? This will attain 1000 degree much more rapidly, okay, than the concentration does in the system itself. So within maybe 10 minutes or 15 minutes you will find, or half an hour, you will find that everything has become, when the carbon has barely started to penetrate inside the solid, that's the time you will see that entire thing has become homogeneous. So the first part could be a problem is a transient problem. Heat and mass transfer both are changing as a function of time. Heat transfer after some time will attain the steady state or the equilibrium state because of this consideration that the thermal diffusivity is high, and therefore after some time, following the introduction of this entire box into the furnace, what happens? Temperature can be regarded as uniform, which is equal to the thermal furnace temperature. So there is a thermal equilibrium between the furnace temperature as well as the box, and as a result of which the subsequent mass transfer operation or diffusion operation can be treated to be taking place under isothermal condition. So at that particular temperature, when isothermal condition, so therefore the surface concentration is also changing as a function of time as the temperature is changing. But once temperature becomes fixed at thermal equilibrium, then the surface concentration is also going to be fixed. It is not changing as a function of time, and then the diffusion is going to start. And this, if you can look at this, is because the diffusion process is slow, so you can apply an unsteady state diffusion theory. You can say that it is an unsteady state diffusion. It is could be, you can do a multidimensional, or if you want to find out that what is the case depth at the center, you can apply a one-dimensional approximation, and you can say that this could be, except of course it is a finite domain. So in this particular region, corner regions, the two-dimensional effect will come, but exactly speaking, this will require, if you want to solve it in a two or a three-dimensional mode, because the actual sample is going to be three-dimensional, okay? So, but we can say that at the center point here, okay, which is far away from this particular corner, it is here that diffusion will be predominantly along the x direction, because this point is away from this and this. So if the length of the sample is higher than the thickness, okay, in that case we can approximate that at this particular point, what is the diffusion is basically taking place in, or diffusion is basically unidimensional in nature, and that allows us that because carbon diffusion is small, so one-dimensional unsteady state semi-infinite geometry, and then the error function solution can be applied. Okay, and then if you have the error function solution, then we can say that look, the solution will go something like this. This is our surface concentration from the isothermal period and this is the initial concentration of carbon, C carbon initial, and this is the surface concentration as a function of time. Okay? And then you can apply the criteria that say what is the case depth, that I want 50% of the concentration. So if this is the height, so this is the 50% of the concentration, and this represents basically the time, 50% of Cs. So at this particular point, you will find out that if you apply, because the one-dimensional theory is applicable here, not here, not here, so therefore you can say that this time Tc will represent the dwell time of this inside the furnace, which will give you, a case depth where you can find out that what is, this is not concentration, this is at a time, and this is as a function of distance. Okay? And this you can find out that at this particular distance, at this particular time, we will have a concentration dictated as from the surface. This is given from x is equal to 0. So that's how the concentration is changing as a function of time. And this is the location at which, so this will say x sub c. Okay? So this is specified at point 1, and this I will find out from the error function solution that at what time the graph really. So this is my desired concentration line, and I can have different lines like this for different time. That's the way this is increasing time. So this point is fixed now, and I say that look, and I say this distance is also fixed because I said that it is 1 millimeter distance or 2 millimeter distance up to which I want to have this 50% concentration. And then looking at this, you find out that it is not this curve, it is not this curve, it is not this curve, but it is this curve which satisfies the condition which you have stipulated earlier already, and therefore you can, from this particular graph, you should be able to find out that what is the exposure time or the dwell time of this particular box inside the furnace itself. If you want to do exactly, solve the problem exactly, then you cannot apply the error function solution, right? But these curves can be obtained by solving the diffusion, equation. So I will write, for example, for an exact geometry, we'll write the three-dimensional heat and mass transfer equation. Even if you consider, okay, so say that's what it is. And then no source, etc. And so if you apply, so you have a 3 x direction, y direction, and z direction. Then we have here mass transfer, and then we have d gradient C. This is the carbon concentration. So these are two equations if you want to, because you want to solve exactly right from time t is equal to 0 when the object is, so you have to solve the three-dimensional equations, and this three-dimensional equation will give you, if you solve these equations, of course you cannot solve it by hand, they are simultaneous equations because d is going to be related to temperature. Okay, so they are coupled equation. Maybe K is related to the composition, thermal conductivity is the function of composition, so they have to be solved simultaneously. You cannot do that solution by hand, you cannot apply the error function solution, but then you have to solve it by a computational method, and then but once you solve it, this will give you, that how concentration changes as a function of x, y, and z. So you know the locations at which you want the carbon concentration to be 0.50, so those locations are fixed. So, and then you will find out that what is the corresponding time at which this concentration will be equal to 50% of the surface concentration. So what is that T? That you will be able to find out once you work out the implication of this model by applying the boundary condition. So if you want to do it in the laboratory, what you basically do, you take a long strip and then you can measure at this particular point, apply the one-dimensional theory, and then one-dimensional theory means the error function solution. From the error function solution, you can calculate the time, and then you take out the sample at that particular time, observe it under a microscope, and then you can compare that, look, I have gotten, if you see my carbon concept, for example, carbon concentration, if you do it at different temperatures, and then you can say that the carbon concentration, if you can measure the concentration, and then one is. So one line could be concentration versus distance. This is also possible if you can measure the concentration at different points as a function, and then you can see that one line is the predicted line, which is based on the error function solution. The other could be the experimental line. So you can verify, okay? Or alternatively, you can have just one point here. You can say that the location at the location where I have, this is CS star and this is 50% of CS star, okay? So I can say that I get at this location 50%, that's my requirement, but I get that this is my experimental point. At that particular point, the theory does not match, or if it matches exactly, in that case I can say that it is, the theory is the round one, and triangle one could be experimental, and then you can just measure one single parameter, that what is this particular distance. So this distance is compared here, and then you can assess that whether the error function formulation works or not. But in actual reality, you will not do it like this. The actual carburization problem has to be worked out based on a simultaneous heat and mass transfer consideration, as I have indicated here, by applying the same kind of boundary condition at all surfaces. Now, the gas carburization and box carburization are essentially not different, in the sense only how you generate the carbon dioxide or the surface reaction that is important in this case. So gas carburization, for example, you use in a furnace CO2 mixture. That is the gas that you use, and that gas you pass over the steel solid sample at a high temperature. Okay? So you can keep the sample in a furnace at 1000 degrees centigrade for a prolonged amount of time till it is homogeneous. Now you start to pass carbon monoxide, carbon dioxide mixture through that solid, over that solid sample. So you can have a furnace, for example, maybe I can say a tubular furnace, and then the tubular furnace may be containing, you may have a specimen here, or maybe you have a vertical furnace in which you have suspended a solid, and then you introduce a carbon monoxide, carbon dioxide gas mixture. And you create the temperature here in such a way that this reaction at the surface will take place, and the gas composition is such that 2CO is equal to CO2 plus C. That's what is the reaction at this solid, it is going to, solid surface it is going to take place. Okay? So that will depend on carbon potential of these samples, that will depend on what is the CO-CO2 ratio and what is the temperature. So you have created the condition in which this reaction is possible in the forward direction. Okay? And this carbon is, we write it as underscore, which essentially means that it is not the carbon here, it is not the carbon which is decomposing. This is not happening, this is a heterogeneous chemical reaction taking place at the surface of the solid, that means at the gas solid interface. And this tells us that we can have an equilibrium because chemical reaction is assumed to be fast, this is conditions are favorable, so this reaction is assumed to be at equilibrium at the surface, so we can write down that what is the equilibrium constant, activity of carbon, and PCO square. We also know that what is the inlet ratio, this is at the inlet ratio, and this inlet ratio, we can expect the inlet ratio to be prevalent right up to the solid surface, because we are assuming that it is neither the boundary layer transport which is important, it is not the bulk transport which is important, but what determines the rate of diffusion, what determines the growth of the carbide layer is dictated by pure diffusion. Actually, what is happening? You from bulk to transfer, bulk from bulk, carbon dioxide, carbon monoxide mixture is going to be transferred to the edge of the boundary layer, then through the boundary layer it will go, then at the surface chemical reaction will take place, and then the carbon will start to diffuse. And what we are saying here, that of the 4 steps that I have just now mentioned, bulk transport, boundary layer transport, chemical reaction and diffusion, diffusion determines the rate of the process, and as a result of which all other steps can be taken to be equilibrium. So, therefore, we can assume that this inlet concentration is going to be prevalent right up to here. Excuse me. If it is so, then we can also apply that PCO, PCO2 at this interface, because this is the equilibrium constant. This refers to the interfacial concentration. These concentrations are interfacial concentrations. So, this ratio is going to be applicable even at the interface. So, if I say this is PCOI and PCOI square and PCO2I, then we can say that this I is equal to this and is equal to n, because there is no gradient between here and here. And then we can say which may be taken to be 1 atmosphere. So, we have one equation here, second equation here, and the third equation here. And we have, as you can see here, this is the chemical reaction, and as you can see here that we have 3 unknowns, PCO2I, PCO and activity of C. We have 3 unknowns. So, therefore, the activity of carbon at the surface of the solid can be determined. And then the problem has now become equivalent to the box carburization problem. So, you can again, if the sample is long, if this side of the sample is much larger than this particular thickness of the sample, in that case you can apply an error function solution, okay, and then find out that how the case depth is changing as a function of the time. So, it is only the evaluation of the surface concentration that is different as far as the formulation of the box carburization vis-a-vis the gas carburization problem is concerned, but otherwise it is entirely the same. The moment carbon reaches the surface, the carburization takes place because of diffusion here also, because of diffusion there also, and under certain approximate condition we should be able to apply the error function solution and find out how carbon profile is changing at a location as a function of time. That solution is possible. If it is not possible, if simplification of geometry is not possible, then you have to consider the problem again in a simultaneous fashion, heat and mass transfer together, or if you want to do an isothermal solution, you do not require this, you have to solve this, but even solving of this equation in a 3-dimensional unsteady state mode will require numerical solutions or computational methods, but you will be able to work out by solving this equation with the right kind of boundary conditions, that how the concentration of carbon within the solid is changing as a function of time, and this will allow you to determine the evolution of case depth as a function of time. The same philosophy applies to the nitridation problem also. Here at the surface, the reaction is this. From the gas phase, nitrogen is getting into the dissolved phase. So, we write it like this, or and again once the nitrogen, this is what? This is at the surface. So, if you have a solid, for example, and you have a nitrogen gas here, and that is, this reaction is taking place at the surface of the solid. The thermodynamic conditions, nitrogen potential, etc., are such that this reaction takes place, and an equilibrium is established between the gas concentration and the solid concentration of nitrogen right at this particular interface. Again, as I have as what we have seen in the context of carburization, that because there is a boundary layer around the solid, so we will assume that the nitrogen which is available in the bulk, the nitrogen from the bulk, it gets transferred to the edge of the boundary layer. Then nitrogen is transported through the boundary layer, it reaches the surface. Then the reaction takes place, and following that nitrogen starts to diffuse into the system. And all these first three steps, the bulk transport, boundary layer transport and the chemical reactions, they are assumed to be known, they are assumed to be very fast, and hence we can say that the diffusion or the rate of growth of the nitride layer in this solid is controlled essentially by diffusion. It is not controlled by the bulk transport, it is not controlled by the boundary layer transport. We will do a scenario where we will, particularly when we talk of convective mass transfer problem, that if you have a solid and then at any point of time, for example, suppose we have nickel oxide, nickel oxide, and this is nickel, and then we have a boundary layer here. So we are talking about in these problems, the carburization, because we are talking of solid state diffusions through dense medium, these are all dense medium. On the other hand, diffusion through solid nickel could be, when reduction takes place, it could be a porous material. So if you consider this particular problem here, we see that we have a boundary. This is the part which I have drawn, this is the solid, initial solid. That's what is this contour. This is what is the gas boundary layer, or the concentration boundary layer, I would say, CBL, concentration boundary layer. And we started with a nickel oxide sphere, and then hydrogen is passed. Then what happens is hydrogen reduces nickel oxide, and this reaction takes place. Nickel solid, this is hydrogen is gas plus H2, is gas at a temperature, high temperature. And in this case what happens? The transfer takes place through boundary layer, then diffusion takes place, because the interface is here. So initially I had a pure nickel oxide. After some time the scenario has changed, some reduction has taken place, nickel has formed, product layer. This is a case of a pseudo steady state diffusion. And here what happens? We see that the gas which is available everywhere is transported through the boundary layer, it diffuses through the nickel, and then it reaches this interface which is the reaction interface, and then the chemical reaction takes place. We will take up this sample and we will not make that idealization which we have made there. We will say that we will assume that all this influences the rate. This is also important. This is not operating close to equilibrium. This is not slow process, boundary layer transport. The diffusion is also not very fast. This is not in equilibrium, and the chemical reaction itself is also not at equilibrium. So diffusion is a slow process, boundary layer transport is a slow process, as well as the chemical reaction is also not at equilibrium. And if that is the case, in that case, the reduction of nickel oxide will be a function of the boundary layer transport rate, nickel diffusion rate plus the K. And there we will have, the rate of the process, reduction process, given in terms of the rate of these three individual kinetic steps. That means 2 mass transfer rates and 1 chemical reduction. So that problem, when we discuss about chemical reduction, gas solid reactions, that I am going to discuss. But this problem we have simplified here significantly in the context of carburization, gas carburization, as well as nitridation, because we are assuming that this transport is very fast, nitrogen is available here, boundary layer transport is also not so important. So whatever is the nitrogen concentration here, that nitrogen concentration is available. It is possible. You can say that, sir, I want to assume that both diffusion and boundary layer transports are important. Okay? Because there is no product gas which is coming out here. So, everywhere it is going to be pure nitrogen gas, you must imagine, and that is the hypothesis of the reason for which it is being considered that whatever nitrogen is present in the bulk, the same nitrogen is available right at the interface. But if you want to say that, sir, there is a difference in the, there is a resistance in the boundary layer, so the overall rate of growth of the nitride layer is no more going to be a function of only the diffusion, but also is going to be a function of the boundary layer, transport through the boundary layer. So, both these rates are going to be important as far as the prediction of the nitride layer is concerned. But in this kind of a problem, because the solid state diffusion is a dense material, solid state diffusion is extremely slow, and that there is no product gas. So, it becomes a futile exercise to consider that there is a boundary layer resistance in this problem. But in this kind of a problem, what happens is that particularly when you have a product gas which is coming out, then there could be product gas concentration high here, which will cause a gradient of hydrogen from here to here, and therefore this can afford some finite resistance. So, it may not be a good idea to ignore that boundary layer transport altogether in the analysis of such phenomena, and I will show you in tomorrow's lecture that we will consider diffusion, we will consider chemical reaction, we will consider this, and to have a combined rate of reaction of the process, that at what rate the nickel oxide is shrinking as a function of time. But for this class of problem, carburization and nitridation, that is not essential. It can be assumed safely that diffusion within the solid phase is the rate limiting steps. All other kinetic steps per se are going to be at equilibrium. So, once you have therefore assumed equilibrium of this reaction, you can now say that, look, my K equilibrium, which can be obtained from literature, is wet percentage nitrogen or activity of nitrogen at the surface, and Pn2 square root, and which is also at the surface, and this Pn2 at the surface is the Pn2 at bulk. So, this is Pn2, and this could be a mixture of, for example, this could be 1 atmosphere, or if you use an argon or nitrogen mixture, this Pn2 could be less than 1 depending on the scenario. Okay? So, I will assume therefore that 1 atmosphere nitrogen pressure is available right at the interface itself, and knowing the Ke, which is known from the temperature at which nitridation is being done, we should be able to find out that what is the surface concentration. Okay? And once that surface concentration is done here, the same approach of diffusion, either it is a one-dimensional unsteady state semi-infinite geometry or a three-dimensional transient problem, you can adopt anything, the governing equations what you have learned, and you can solve those equations in order to find out that at what rate the nitride layer is growing within the solid sample. Okay? And as we all know, the diffusion within the diffusion coefficients is of the order of 10 to the power minus 8 meter square per second. And I have given this is the diffusion coefficient value, and therefore square root, we can understand that this represents basically a penetration distance. Okay? And this value will come out to be extremely small. So, even though this could be few millimeters or few centimeters thick, it is unlikely that the nitridation layer will penetrate up to the center. That perhaps is not going to happen. Nitrogen is going to be restricted mostly to the surface if you do nitridation process for several hours, okay, and that will give you the necessary required surface hardness. So, you have to have an idea that till what depth I require that strong hardness. These are already the design criteria, and then you have to control the process parameter in such a way, and in this particular case you will control the partial pressure of the nitrogen, you will control the temperature of the furnace, and then you will carry out the nitridation process for a given or stipulated time, such that we can have the correct amount of nitride layer at the surface, which will protect the surface from abrasive degradation. The other process that one considers is where we will find application of the diffusion. There are many actually, we can go on and on, okay? And we will again come in the context of this, when we will discuss not exactly this problem, but iron ore reduction problem, when I will demonstrate, we will see the diffusion again through the solid product layer. Okay? So, many problems are there. One such interesting problem where diffusion is very important is also the galvanizing problem. I am not going to write the exact, the process only I am going to explain to you. Galvanizing, hot dip galvanizing process, for example, you may be knowing. Okay? You produce hot rolled coils, for example. Those coils you may have seen when you are traveling, a big truck carrying about a 12-ton, 15-ton coils, one single, and those coils, hot rolled coils, basically are moved through a zinc bath with a certain speed. And then what happens is that if you have a plate like this and it is moved through a zinc bath at a certain temperature, then what happens? A layer of zinc, this is an exaggerated figure, this could be not even millimeters, okay? This could be micrometer thin. This is the zinc, and coating is on the both surface, so you can have. So when you move a plate at a certain speed through a zinc bath, then what happens is, if the temperature is right, then this is drawn with a speed, then we have zinc layer solidifies on it. So the moment put it into liquid and it comes out of the liquid bath, that what happens, zinc solidifies. But what happens, zinc has finite solubility into steel also. So this is my steel, and as a result of which, what happens is zinc tends to go inside. The bonding of zinc with iron is through the diffusion of zinc into the body of the iron, where chemical reaction takes place, and chemical reaction makes the zinc produce with iron some intermetallic compounds. So this is a combined solidification problem. So there is a fluid flow part involved in the whole thing, because the zinc plate will come, there is a huge bath in which molten zinc is kept. The hot rolled coil comes, enters the zinc bath, and then it travels, and then after some time it goes out of the bath. So there is a fluid dynamics which is involved. Because of the movement of the plate, there is some stirring in the system. Then there is solidification which is involved because of temperature, and then the liquid zinc itself starts to diffuse into the solid steel. That is also another aspect of it. So this part, the bonding part particularly, okay, where zinc diffuses into the iron body and forms, because of chemical reactions, certain intermetallic compounds, okay, this is of interest. That what is the thickness of the diffusion layer, which really, both the thickness, this is also very important, the zinc layer, protective zinc layer thickness, as well as the region over which you have diffusion of zinc, that is also extremely important, and in determining the penetration of zinc, because it is now the diffusion into a solid, the same kind of theories that we have learned, okay, can be applied. Okay, based on the Fick's law, second Fick's law, and cylindrical coordinate, Cartesian coordinate, whatever it may take, and then you should be able to find out that to what extent zinc has penetrated and what are the various kinds of products that have, or intermetallic products that have. If you look at, for example, two-component system, then diffusion with chemical reaction, then what happens is you have the equation can be written something like this. Steady state process. That is the characteristic. If you take a two component system, so this is A and this is dB and this is dxa. So in the medium where diffusion is taking place, chemical reactions could also be simultaneously taking place there. Okay? And this maybe, we can generally say that A plus B, if you consider a second order reaction, giving rise to another. So we can say that Ra, basically, the rate of reaction could be something like C, because I want to write it in terms of mole fractions, so I would say the rate constant, okay, K into C square into XA into XB. So product is being generated, okay. So this is, and here what happens is I will put minus, because the concentration of A is decreasing, B is decreasing, and both of them decreasing, and the product AB is increasing. So I have written in terms of XA and XB, and this is CA and CB, and that's why when I write XA and XB, this becomes, the C comes here. So we can put it here, and therefore we can say that this equation will look like now K C square. The problem becomes now complex. You require, so you can take diffusion of A through B, or you can take the interdiffusion coefficients which you have learned, DAB. And as you can see here, these reactions 1 and 2, if you are talking of two component systems, iron zinc for example, in that case you will find that what happens is these two reactions are mutually related. So they are coupled equations actually, and that this is, you require of course the rate constant that has to be supplied to you. It cannot be an unknown. There are two equations and only two unknowns could be there, and those unknowns are XA and XB, but that the source term depends on the concentration. So therefore we find out that this brings in nonlinearity into the system. So these are coupled ordinary differential equations which are essentially nonlinears, and they cannot be really solved by analytical methods. But this is the way one can really incorporate chemical reactions into the diffusion. So within the domain of diffusion, if reactions takes place, that is the way one can incorporate, and that sort of a physics may be needed in order to find out that over what distance the diffusion is really taking place. It is not just pure diffusion, but the diffusion is. So for example, one can also say that carbon diffusion, if you want to find out that carbon is reacting with iron, and then in that case, in the context of gas carburization also, you should be able to find out, you should be able to consider the rate of the reaction. And these solid state reactions are very, very slow actually, okay. They are as slow as the diffusion process, so they may affect the concentration profiles. So, and again, these reactions may be associated with some kind of a heat generation or heat consumption depending on the particular specific chemical reactions in concern. So therefore, what it turns out that this is, what it means is that within the domain of diffusion there is an influence in the concentration profile because of the chemical reactions, and this may be a case in the in the context of galvanization. And galvanization is not purely a diffusion problem. As I said, it consists of some part is fluid flow, some part is solidification, and third and the last part is the diffusion. All three, so it's a multi-physics problem, more complex than actually the carburization and the nitridation problem. So we'll continue with this.